Come on. Yeah, the firsts are like a fun little thing. Oh my god, is YouTube gonna be like this? No? Okay. Now we're good. I thought it was really fun, Spectry. I had a headache for the entire rest of the night. It's not even like a normal headache. It's like a brain ache that I've had before, like when I was a tutor doing calculus for 6 hours in a row, and it was super busy. Like when you think that hard for that long, it just like it makes your brain sore, like it makes your muscles sore. But other than that, I thought it was pretty fun. That one that one puzzle I stuck on for forever. I thought kind of had a BS solution, but um. Aside from that one puzzle, I did enjoy it, and that the very last one was pretty fun. The puzzles weren't as good as like the base game, but it's a mod, so I don't really expect them to be as good. But they're still fun in their own right. Okay, I'm gonna hop into the voice chat, see if Finlux or any others want to join. If not, it's completely fine. Yeah, for the first few hours, I've been doing the physics stuff. So I did in one sitting. I was definitely pressing myself to get through it in one sitting. I probably technically should have like, done it in halves, and I would have felt better, but too late. Oh, hey Finlux. Have more revelations on how to teach 3 separate preps in the same 6-hour period as a similar challenge? Oh geez, I bet Obi.
Hi, Don.
Okay, hey, I got you now. How's it going?
Pretty good. How are you?
Doing good too. Hey, so I guess for this group, you mentioned like being interested in doing something related to coding, or do you just want to do some normal problems? I don't mind either.
I don't mind either. I mean, if it was coding, yeah, I mean, it was something I mentioned on a spur of the moment, but I don't know. If you're interested in doing it, we could, but it's, thinking on it now, it seems like it's hard to do. It might be hard to do through this medium, right?
Yeah.
I don't know. Yeah.
Maybe for now, I'll just do some normal problems. I don't have a particular idea for like what to code either, but it's always something I'm open to.
Yeah.
Let's see. Actually, I should have the images still saved. The problems that I was interested in, at least. Okay, yeah, we did that one. Oh, okay, here's an image charge one. Number 12. And I put the link for the Excalibur on the same like spot as normal with the voice chat, like text chat.
Yeah. It's been just long enough for me to forget how to find that now.
You right click on like the header for the voice chat, and there's an open chat button.
Open chat. Yeah.
And then the link is right
Oh,
there.
I see. Yeah.
It's a really weird place that Discord has, but in terms of like who should have access to the link, that's like the best place I can think to put it. Nice. Majestic seahorse. um, so a point charge Q is located between two parallel infinite conducting planes, a distance d from one and L minus d from the other. Where should the image charges be located so that the electric field is ever perpendicular to the planes? Huh. God, this marker's so thick. Go to that one. So this is not necessarily centered. So they say image charges, so we need to place multiple image charges. So the electric field is everywhere perpendicular to the planes. So this might be too obvious of an answer, but what would be wrong with another charge, I guess minus q, a distance d away in this direction? And then another minus charge q, L minus d in this direction.
Yeah, that was my immediate thought. The only thing I was wondering is, do those two minus Q charges interfere with each other?
It could be like, we might want to do like over 2 or something.
Hmm.
Maybe a sneaky way of doing this would be to put another image charge, hey Dwarfkek, right here, distance d away, and then you wouldn't have to do this over 2 thing. And you'd have to move the, I should do this in a separate drawing to keep these ideas separate. Copy, paste. So maybe a different way is to do 3 image charges. With the idea that these 2 positive charges, like they're gonna act as a barrier against each other, where the field lines are kind of gonna like point like up and never quite touch, and that will like potentially prevent like interference.
Oh,
I was trying to make like a little like barrier between the 2 halves here, I guess.
yeah, I think that's perfect. I mean, I'm totally sold on this answer.
Okay.
No, I think it's great. I mean, how could it possibly? I think it's because it's perfectly symmetric, right? So how could it not be perpendicular to the planes everywhere? When I read the problem, I thought it meant the field had to be like uniform everywhere in space, but I guess that's not what it means, right? It means just on the lines of those planes, it has to be perpendicular right at that point.
I think so too, yeah.
Hmm. Yeah, because isn't this like, hmm. I mean, should we go through the effort to try and pick a point? Like, I mean, everything's symmetric now, right? So we really only had to pick one point. I don't know if we want to grind through some algebra to show that
Oh, to
the field
calculate
would
it?
be hor. Yeah, I don't know. Do we want to?
How hard?
I'm saying, for example, pick a point like
I don't think
how do
it'd
I
take
draw
that
the
long.
point? Like if I picked a point right here, right,
Yeah.
and call it, well, anyway, but I want to find all the, what do I want to do? I want to find all the vertical components of the field at that point and show that they add up to 0.
Oh, right. Yeah. That wouldn't be that hard.
Actually, is it? Actually, now that I look at it, is it going to work? Because I see the two charges closest to it will cancel vertically, but the two far out to the left, I don't think those are going to cancel, are they?
They might not. You're right.
Like this way, no, this way. Sorry, I'm doing this all wrong.
Hey, Fizzbuzz. Okay, so you didn't see the initial problem. It's we're given this initial charge Q on the right, and we have to place 3 image charges so that the field lines are perpendicular to these conducting planes. And so this one appears our first instinct to place minus Q over 2 charges on either side, but the answer we're currently looking at more is this one, where I should have done a better job of marking the image charges. That's an image charge, that's an image charge, and that's an image charge. So we're kind of like trying to verify that. But yeah, so we're placing 3 image charges, and this one we're investigating. But yeah, if we take the origin to be like halfway between the 2 conducting planes, I think we could do some algebra there. Well, maybe.
It doesn't seem like it can work.
Yeah, I'm trying to think, like this, the 2 charges on the left, they do, I guess we could think of them as a dipole, and their contributions on the right side are going to fall off pretty quick.
Oh, Don, wait a second now.
Oh yeah?
Wait a second now. Isn't it true? I got a question. So let's think about the point that I marked, right?
Yep.
The point that I marked, and I want to know the image charge that you placed on the left-hand side of the left plane, right?
Yeah.
Is that charge going to produce a field at the point I marked?
Oh, you're thinking about the conductor physically blocking it.
I'm thinking about that thing they called shielding, right? So does the electric field get blocked by that conductor?
I think for the image charge argument, we have to ignore the conductors existing. I think we can't consider them both at the same time. But if that was the case, then yeah, I think we definitely would have a non-zero y component at that point. But I think we can't. We can only consider the electric fields produced by these point charges here. Oh, and if this was the entire point of this is to be a discussion, so it's like a reading that we've been doing on Saturdays. So I mean, I guess like maybe don't just like blurt out the answer if you know it, but feel free to like give hints or extra questions to like help the discussion.
What did they say in the chapter? Didn't they say that when you had a conductor, that the electric field lines always came in at right angles to the surface? I thought they always came in at right
yes,
angles. So
they do.
well, if that's the case, then why do we have to put down any image charges? Oh, just so we have a field on that field outside?
What's the point of? the point of putting down the image charge in the first place, is to figure out something about the conductor. So I think we don't necessarily know how the conductor behaves until after we've done this point charge work. But you are right that whatever, like the charges arrange themselves such that the electric field is always perpendicular to the surface of the conductor. But we don't necessarily know exactly how that field looks until we've done this point charge work, I think.
My computer froze.
Oh no. Were you able to hear that last part?
Yeah, I heard you. I
Okay.
got two computers going. I get the one with Discord is working fine. I get the other one that I'm trying to read the textbook on, but the window froze up. Maybe I got to refresh it here.
Oh dang.
Yeah, because I was trying to run back to earlier in that chapter when they were talking about they had like 5 rules for a conductor, right? And what was going to happen at the surface of a conductor, with respect to like the field lines and oh, maybe it's back. Maybe it's back. Yeah.
But I don't think we're supposed to use any properties of the conductor itself.
Could you say it again? You don't think we're
Or,
supposed to do what?
I think we're supposed to ignore the existence of the conductors if we're going to do image charges.
Oh,
Because I think the entire point of it is to figure out the electric field produced by the conductor, so we don't like know anything about it yet. I think a truly symmetric arrangement is on the right track. Okay, that's what FizzBuzz says. And I think they don't necessarily have to be point charges. I assume we could do like an image charge distribution.
well, it does say charges, so I guess you could have as many as you want.
Yeah, I don't necessarily know that idea helps, but
But why does it tell us that planes are conducting then?
um, I think it's so you could figure out how these conducting planes are going to behave. Oh, the angles for this. If I want to actually do this calculation of the point that you named, the angles are kind of annoying here, aren't they? Hmm.
Very open-ended question. It feels like all the charges we put down should be on the same horizontal line, doesn't it? Like through the one that they gave us.
Yeah, I definitely don't have any ideas that would like not be all collinear. Or like I guess all like horizontal is a better word.
Is it kind of like a superposition problem? I want to think of the two right-hand
Oh,
charges and the two left-hand charges and kind of superimpose the two problems on top of each other.
so I mean, in the book they do the example for the image charge with just like a single conducting plane and a single point charge.
Yeah,
And the answer there is just that other point charge minus q, the same distance away.
yeah.
So, Mean Machine Rex, thanks for the follow. If we the superposition argument make me think it's what I just put for like that second answer, but maybe it's not. But I think you're right. The y components for the two charges on the left certainly aren't going to cancel.
No.
But I feel like there's an argument to be made about just it being small enough that it doesn't matter.
Oh yeah, I don't know if I buy that one. I was thinking
uh,
maybe find the right ratio of charges, but I feel like if you tinker with any of them, it's going to mess up the other ones, right? I can't see any way to get a good ratio with those four like that.
right.
Hmm.
Hey, Stephen Armstrong. Texas is better than California? I mean, depends on the person. If you enjoyed like 100-degree days all summer, more power to you.
What about the first idea you had, right? Where you had the minus q to the right, there was a distance d, and then the minus q to the left, there was a distance L minus D.
Mm-hmm. I mean, this is basically, we could work it out just like a chapter one problem. I wonder if this like little bit of asymmetry with the L minus D versus D would mess up the Y component cancellation. Could we, instead of doing like Q over 2, like we could make it like minus Q times a constant and work out what it must be. Well, we'd have two constants.
Okay, and maybe the
We get
constants
two
will have to do
equations.
with,
Okay.
maybe they can be in terms of D, maybe.
Oops. I do. eh, Cross that. Oh yeah.
What if,
What? Oh, sorry. Go
I was,
on.
I was gonna say, what if what if the problem they gave us had the point right in the middle, right? I mean, what if it was already symmetric and it was right in at the midpoint between the two plates? Then would we have an easy answer? I still feel like I'm not sure it would. I still don't know if we'd have an easy answer.
Hmm. I feel like I would have said they're both minus q over 2 equidistant apart and not thought about it much harder. If it was right in the middle. I think that would give you hyperbolas or some weird shape, BizBuzz says. For the equipotential. I guess I could see that too. CXMR, thanks for the follow. So we'd have two unknowns in this situation, but we could get two equations because we could set the y component to be 0 at both of these dotted lines that I drew. It's like e sub y at any point like d comma y. It's gonna be an annoying geometry problem to get the angle from like the farther away charge to whatever arbitrary point, but other than that, I don't think it'd be too hard of a problem to work this out. Oh, k is a terrible choice of constant.
I'm just filling my coffee cup. Be right back.
No worries. Just column C. Let's say Q. Oh man. Okay, fine. And 3 and 3. Okay, that's how we'll name things. So this first one is from 1. CXMR, I was switching like my normal kind of like math type of stream, which for me is I take questions from chat and internet. The emphasis is like homework help. And if there aren't questions from chat or if there aren't people in chat who need help, then I usually just like look for them, look for questions either on Discord or I'll do a study question from a book. Love it. Yeah. If you're interested in math streams in general, let me link a bunch more to you. Because a whole little community of us who stream math, and we all have our own styles, and some of us like play games and all that good stuff. It's cool people. I mean, I guess these don't have to be. If we're having a constant in front, we don't have to get those subscripts, do we? You're a senior in college right now studying mathematics education. Oh, cool. In that list of people, if you want to talk about math education specifically, e to the 2i pi is great, and Simplex Wachinko is great. They're both super interested in talking about math education specifically. I also would talk about it, I just don't know all that much about it. I forgot my sine theta. Do you drink a lot of coffee, Finbox? Or is it's probably a little late in the afternoon for you?
Yeah, I figured I'd put some coffee on to see if it would help me be more smarter. So we'll see if it works.
Okay. I like it.
I didn't make any this morning. I don't know why. So I don't know. But actually, yeah, I do. I drink a lot of coffee.
Okay.
Coffee and tea, kind of live on them.
Nice, yeah. Um, I have to figure out what this angle is over here now. It's annoying. Well, I could say arctan. Y component, I'm just calling y. The x component is 2L minus D plus 1D. I feel like there's probably some better geometric argument to make here, but you know, why did geometry can have sine of arctan? Great.
I actually really like this problem. I just don't think I'm quite understanding it.
Yeah, I'm glad to get an image chart problem in there because I like that they make you be a little bit creative to solve them, but I definitely could be off on the wrong foot here. Sorry, what?
I mentioned last week that when I read that chapter on the section on image charges, I thought it was really interesting. It was really cool. But the one thing I didn't like was I felt like they didn't define what an image charge was. They like the section was called image charges, and then they said, well, we're going to put this other point down here. And I was like, okay, well, I guess that right there is the image charge. But then I wasn't sure if it was supposed to be imaginary or if it was real. I guess it was real. For some reason, the image charge sounded to me like it was going to be something that wasn't really there, that you is just some kind of a tool you'd use to do something.
I think it is a tool you use to do something. All we actually have in the problem I'm working on is the point charge in the two conducting planes. But we don't necessarily have a clean equation like Coulomb's law to figure out how the conducting planes are going to behave. And so I think we like use this image charge thing to have something we can actually calculate.
Yeah, wait, now that does sound right. I think that is what I was thinking. So wait a second. So the one they did in the chapter, right? I mean, there was an infinite conducting plane and there was a point charge nearby, and they wanted to find the field lines at the plane, didn't they? Isn't that what they were trying to do? And then they said, well, how are we going to find them out? And they said, well, no, I probably should read it again. It made sense at the time.
Yeah, because like the picture looks a lot like a spider to me. That's what made it like stick out in my mind.
Yeah. So let me ask you this, if this is your understanding. Is the understanding that what they're trying to tell us here is that the field produced by a point charge, the electric field produced by a point charge when it's within when it's close to this infinite conducting sheet, is the same exact field that would be produced by the point charge if the sheet was replaced by an opposite charge, like the same distance away on the other side of the sheet?
Uh, I I think so. Yeah. Hey, Brian. Like I went up to left here, just like draw a quick picture.
Yeah. Does that sound right? Did my
Um,
question make sense? Did I word it well?
I think so. Like if we're interested in like a positive point charge Q in just a single infinite conducting plane, we
Yeah.
can figure out that in the book they basically figured out that. Oh, thank you, Brian, for the 10 bits. That this is that like whatever region of the conductor is gathering up the charge, it has basically total charge of minus Q, and I think the field lines are more or less like a dipole. Not, I guess not exactly because they have to be perpendicular to, well, yeah, I think it basically forms the same field as you would have with a dipole, but only like it's cut in half. You don't have the other field lines that you would have from the if you had a true like dipole. So I think the book found an equation for like the red portion of the field here. Isa sub z. And I think that's why you
Yeah,
would use image charges. Oh, what?
I was just going to answer the chat question about capacitors. We were in the chapter. I think this chapter is talking about capacitors a little bit, right?
Yeah. And so working on this problem 12 here.
They
So
didn't get too far into it. They didn't do like dielectrics or anything yet. They're just
yeah,
talking about capacitance as a concept, I think.
right.
But they
So
did talk about the electric field between parallel plates.
right, yeah. Um all right, I think another way of thinking about this image charge thing is that if a conductor has constant potential, you're trying to name an image charge that has an equipotential curve that matches the shape of the conductor. I think it's a part of the reason why you do this. I remember they made that point. Yeah, like they did the calculation for like the charge produced by a disk, and they said
Yeah.
that from those equipotential curves, we now know the capacitor in any shape that matches the ellipsoids that it generates.
Yeah.
Hmm.
I think I'm starting to understand the image charges better. I think it is what I said. I think it's like you get the same exact field from the point charge to the conducting surface that you would in the problem they did in the book, as if we just had 2 point charges like a dipole, like you said, right? And it's like half of that field from the dipole.
Exactly, yeah.
Yeah.
Because there's no field on the other side of the conductor, but they otherwise match.
Yeah, and I think everything you drew, so everything you drew on the left-hand side of this last picture, like over here, that's sort of imaginary, right? That's not real. None of that's really there. That's just sort of, yeah.
Exactly. Fake. Lies. um, I feel like there's some like similar thing that we do somewhere in math that we could relate this to, but I can't quite think of it. Between infinite parallel plates of uniformly distributed charge, there are equipotential lines parallel to the two plates, and thus the field goes directly from one plate to the other. Oh, okay. Oh, yeah. I didn't think about that, like field lines and being perpendicular to equipotentials. That situation. But yeah, that makes sense.
All right. Okay, so now I'm starting to get my head around this question a little more. So what we're really being told is that we have these infinite plates, we have a charge in between them, and we want to place down some other charges in space so that the field lines are everywhere at right angles to those two planes where the plates are. I mean, I know that's been the question the whole time, but I'm just trying to think of, just trying to like restate it now that I've got more of an idea of, I think, what we're doing.
Mm-hmm.
So, you know what? Now that we've said that, I want to say maybe we do need some more point image charges off of this one single line, right? How are we ever going to get it to work if we keep all of our charges on the same horizontal line? Now I'm thinking maybe we can put like the corners of a rectangle around. What about something like that?
Can you? I don't know what rectangle will be helpful, but can you like draw it?
I drew a picture off down to the right.
Oh,
let's see.
Okay,
yeah. So what about if I thought about this here, like this rectangle here. So if I put charges at the corners there, let's see what that would do. I'm just trying to use symmetry again. What if I make that minus and that plus? Right now I'm only looking at the right side, the right plate.
Okay.
So I've got a rectangle here. This is the top of the rectangle is 2D. I mean, that looks okay, right? I think those four charges should give me a horizontal field everywhere on that vertical line that bisects that rectangle, right? Are we convinced of that? I think so, because it's sort of like two dipoles, isn't it? It's a dipole at the top and a dipole at the bottom, and one of them's flipped over with respect to the other one. I think that works, but it only works for my right hand side.
And like,
plate.
what if are we creating the same problem like somewhere up here? Like, are they still going to cancel there?
I think they would.
Or how's this fundamentally different from just having the single Q and minus Q pair?
Yeah, good question. I don't know yet. I don't know why my brain's thinking of this. I just want to follow it a little bit.
No, it's worth exploring or exploration.
What about if now at the bottom here, this is L minus D, these bottoms here. What if I just do this? I put another Q, positive Q here. Positive, and I wrote negative. Oops. Oops, got it.
And Brian, maybe you don't like straight up spoil it, but like if you want to give hints or like help guide or ask discussion questions, please do. And hey to Kobe on YouTube as well.
Yeah, I don't think we're completely stuck yet. So don't just tell us the answer if you can. But certainly, if we're doing something really dumb, then if I'm doing something really dumb, then let me know.
Generally, you want to avoid having image charges in the region which you want to find the field.
Oh.
So, I mean, is that just saying that we don't want to put an image charge right on the conductor? I don't think we're doing that. Maybe I'm misinterpreting you. LSD princess. Yeah.
Sorry, I'm still getting used to this. I moved this. Keep going.
Lokstall, thanks for the follow. The red minus Q above in the plus Q seem like a problem because that's in the real region between the conductors.
Okay, let me read that. The red minus Q above the plus Q seems like a problem.
Oh, so you're saying anything, putting any image charge between these two conductors. I'm not sure why that would create a problem, but I can believe it. So that would say that this other idea that I had here isn't good either because I had that positive Q point charge or image charge. Thanks, Brian. In terms of like, I guess making a singularity in the region that we're interested in. Hey, Joseph.
Yeah, this is yeah, let's play around with this a little more. So maybe okay, let's erase this one, this one, this one. What about a bigger rectangle? Oops, really thick.
I know it's okay, Brian. It's a little bit hard to like respond to chats instantly, but 20 is the biggest number ever clip. I don't think I've seen that. I can give it a watch after the reading group. Oh.
Not coming out very well. What's this? I have to abandon my picture here. It's not coming out very well. I'm trying to make a, okay, let's see. I'm trying to make a rectangle. I can probably get one here, right?
Yeah, there should be a rectangle tool somewhere. Yeah, like number 2. Oh, it's a rounded though. Oh, there's an option to make it square. Yeah.
Well, rounded could work.
I guess it doesn't matter.
Wow, now I got something funky going on. Stop, stop, stop. Look, my charger's here. So here's D. Here's L minus D. Could I get image charges at these 4 corners? Is there anything to be gained by thinking about these 4?
Oh. I haven't quite worked it out, but I get the feeling that the potential might not be constant. Like I feel like I'd be doing potentially more work down here versus up here. I don't know that the conductor being equal potential in this case. Because like I guess I'm all the way down here, all 4 charges are working against me. But if I go up a little bit, they're somewhat canceling.
I really like that little idea I had with the two dipoles, you know, like a plus minus and then a minus plus underneath it, kind of staggered. I felt like that was an idea that might get me somewhere.
I don't know, I'm still not convinced we need to go away from the horizontal line, I guess.
You think we do or don't?
I feel like we can keep things as a horizontal line. I don't see why not yet.
Okay.
I was kind of still pursuing that setting things equal to 0 as like a little algebra check to figure out what the ratio of the charges should be, but it's a little bit annoying.
Yeah, so you got 1 plus 2 plus 3 has to equal 0, right? I mean, those
Mhm.
three terms, the sum of those three terms.
Right.
And we're trying to solve for C2 and C3.
Yeah, that's that's the annoying part, I guess. I forgot my K's. I mean, they all cancel anyway, but it'd be a really annoying system to actually solve this, though.
Yeah, you know, I feel like this is a geometry problem. It's kind of like that one we did before where we had the two dipoles and one of them was vertical and one of them was
Oh,
horizontal and they were centered at the same point. Remember? And we had to find the field at a point far away from it.
right.
And we did all that work with sines and cosines and wow, we had some trouble. And then they had an answer in the back that was just beautiful, you know, just thinking about like just changing the yeah, you remember that question? God, that was a nice question.
I don't
That's my
remember how the
favorite
book did
question
it.
from this book. That's my favorite question from this book so far.
Oh,
They had they had this and plus minus plus minus. Is this how it was?
I'm looking for it. Um, they don't actually.
Yeah, there it is. Cross dipoles, beautiful. And then the trick to it was don't think of the dipoles as vertical and horizontal. Think of the two dipoles as at 45 degrees, you know, like parallel to each other. Like just change it. Just change the way you look at the dipoles. So you got the same Q but a different D, right?
Um, oh,
There it is,
right.
yeah. So I feel like the problem we're doing right now is going to have some kind of beautiful trick like this. We just have to come up with the way of looking at it. And
Okay.
it's got to do with symmetry and it's got to do with this ratio of like the D to L minus D.
Brandon, what is the definition of an image charge? I don't know if they actually define it. Let's see what they say about them. So they're dipoles I didn't want to cue, Joseph says. Ugh. They kind of construct like the idea of what you're doing with an image charge. I don't. They basically just like are naming whatever other charge has to exist to give you the few lines that you want.
Yeah, I'm gonna have to read that section again. I'm trying to remember what the actual game plan was. Like, What were they trying to look for? Were they trying to look for the electric field at the surface of the conductor?
I think yeah, like they have the expression for E sub z, and I think it's valid for any z. We can calculate the field strength in direction at any point by going back to the two charge problem and using Coulomb's law. Yeah, so they figure out the field at any point for the charge in the conductor by looking at the two charge system with image charges.
Yeah.
You have a hint? I think we're willing to take a hint, Brian, so feel free. Okay. So yeah, that I guess that's something that I was like thinking about with these like C constants. I guess they don't. Yeah, I was imagining a queen number like in integer, but I guess they don't have to be. I assume if you were to do the work in solving the system, you could actually find the ratio. I wonder how bad it'll actually be if you get a lot of like cancellations. But the idea that I had was to get like two systems of equations here. And instead of D, we would take. Oh, is L minus D a positive number? I might need to put a negative sign in front of that. L minus D is positive.
Yeah, it should be.
Yeah. And then like this one for two. Oops. This dang program. Angles are different. Like I think you could do something like this and figure out exactly how big these charges have to be. So I think it's the way that I'm most sold on to pursue this problem. It's just an annoying amount of work to actually solve this for C1 and C2. I feel like the book is going to have some creative way of not having to do that. Another hint? Okay, Brian. Like, it's finding me the right track, guys. It doesn't necessarily have to be like this is something I put here, but I don't know what else it would be if not something like this. Makes you want to cry, Paul. You could keep the charge amounts fixed and try to that one happened quick. The last time we did this, it never happened. Let's keep going with this board though. You can keep the charges fixed and vary the distance, I guess. That's probably worse. It's a 2D problem, but it is not a 2D solution. I really don't see that because I guess like I would think it's symmetric if you were to rotate this, unless the solution that we're it's supposed to be not symmetric. Oh, I mean, I do imagine there's multiple ways to do anything involving image charges or most anything, but hmm. Well, I'm trying to like maybe a 3D shape then, like, but I don't think an infinite sheet of charge is necessarily going to do the trick. Or maybe it will. No, yeah, I don't think a sheet of charge would do it. You like the C2 approach. Hmm. Hey, Krim. I don't know. This is Purcell and Morin. Uh, right there. I don't know. I just want to get maybe the system set up and see like, do we get a lot of cancellations? We just subtract them off or something. This might end up being a waste of time, but it isn't 3D or 2D. Oh, one dimensional. I guess I was keeping it to be 2D to make sure that we actually do get cancellations along the entire conducting plate rather than just at a point. But it should also be true for the 1D case, which could simplify the calculations. Crim, it's a little bit hard to like the example the book gives for using image charges is if you have a positive point charge Q and a conducting plane, and you want to find the field that they create, you can use an imaginary charge minus Q and look at the field lines, and that minus Q charge is called an image charge.
Yeah, so they wanted the field to be perpendicular to that conducting surface at every point. And then they said, well, if we remove the whole sheet of took the conductor out, and if we just put another charge down here, you know, at equal distance from it, opposite charge, that will give us a field that's perpendicular to that surface at every point. And then they argued, didn't they, that that means by uniqueness or something, that means, well, this has to be actually the way it works.
Yeah.
And it feels like now we just have to, we wrote this problem down and in like 5 seconds we had a good guess on it, I think. And it just feels like it's not quite there though. But it seems like if you split it into two smaller parts, that was my idea about superposition. Yeah, and then you said, okay, let's make them both q over 2, right? You had minus q, and then you said, well, let me make them both minus q over 2 and minus q over 2. And it
Yeah.
feels like that's kind of like taking that q charge in the middle and splitting it in half, right? And imagine half of it goes with the one problem and the other half of it goes with the other problem. So is that just going to work? But it feels like those two problems interfere with each other when we subsequently try and use superposition and put them down, next to each other. It feels like they're going to, because the left-hand problem messes up the right-hand plane, doesn't it? And the right-hand problem messes up the left-hand plane. It seems that way.
Yeah, I feel like they don't have to if we like allow this constant thing to like not necessarily just q over 2, but if the one that is further away is weaker, that might be helpful.
Yeah, now you're saying we have to solve for C2 and C3. Yeah.
So yeah, I guess that's why I kind of like this path. I don't know that it's going to work.
So
though.
Are C2 and C3 going to add up to 1, Don? Is that the idea?
That would make sense. I didn't realize that, but I think so, yeah.
Yeah, maybe so a sum of two numbers that add up to 1 and their ratio is like d to L minus d. I'll bet you that's what's going to happen, right?
Yeah. That would make sense. And I think we like I think Brian said that we could. I don't have to do this two-dimensionally like I'm doing. We could just make it a 1D problem and get the same answer. But I feel like I already wrote all this down.
So let's say L is 3, right? Let's think of just some small numbers. What if L is 3 meters, and D is 1 meter, let's say. So the charge is 1 meter from the right surface and 2 meters from the left surface. So then what do we need? We need a 1/3 and a 2/3 Q. So like, I don't know. I just still feel like it doesn't work.
I mean, I'm willing to just bring up the answer and not do this tedious calculation to see if it's actually going to get an answer that makes sense. But if it's not the thing that I'm doing here, I don't know what it would be. Gaussian flat surfaces for 2 points trapped on one side plus symmetry.
Points trapped on one side. Oh, wait. So Gaussian surfaces. So could we just could we put a Gaussian surface like right where that conductor is, like an infinite plane?
Can you have a Gaussian surface that's a plane?
I don't know. I'm just wondering.
I don't know either.
I know they're usually like cylinders and spheres, aren't they?
It might not have. I remember the book gave him an explanation for flux that just involved water moving through a square.
Yeah.
I wonder if it's. I guess a surface integral does it. I assume it could just be a 2D shape. Maybe not. I don't know. Hey, Bev. I know. I'm kind of getting into just wanting to check the answer. So I definitely don't know how to apply Gauss's law here in a helpful way. And check my answer before saying more. Okay.
Yeah, maybe Brian's got it worked out.
The image search questions are fun in terms of like being creative, but
This one here, I'm really enjoying. You know, it's just a really good. It's like a puzzle. You know, I like these kind of problems where it's like you feel like if you just look at it the right way, it becomes trivially easy. I think it's going to be like that. Maybe not.
probably. I mean, it's been a trend with this book that we do it the hard way, and the book shows the easy way. So I believe it.
Yeah.
I see that the next one in book 13 is a 3-star image search problem with 5 parts. Jeez.
Five parts and it takes 5 hours.
Yep. Oh, and there's a dipole question. Oh, it's 3 stars though. Oh. Show the external field if you have a conducting spherical shell in a uniform electric field. The charge on the shell will redistribute itself and create a sort of dipole. Show that the external field due to the redistributed charge on the shell is in fact exactly equal to the field due to a dipole.
That's interesting.
Yeah, it's 3 stars, but that could be a fun one. Do you have any more thoughts for 12? Brian might name it, but I'm kind of like, I'm only looked at the first part of the answer. Oh, Brian was wrong. Oh no.
Oh,
Are you okay with looking at the answer then, or do you want to keep on thinking about it? Or I can look at the answer like later on my own time. If you don't want to see it and you want to like think about it more.
So you're still convinced that we can do this with just 2 charges, right? I'd kind of lost hope in that. I felt like that could never work.
I see what you're saying with like they interfere with the other one. I don't see what else it could possibly be though.
Yeah, I was thinking they would interfere with the other one, but Maybe there is a way to get the ratios to work correctly. What if it was, again, what if it was a simpler problem, right? What if because when you get a problem like this, sometimes it's nice to try and like make it easier on purpose to see if you can find a way to solve an easier one. Like if we moved that charge in the middle right to the center, right? So everything was symmetric. The problem is even then I don't know if I can't think of how we solve it then.
Yeah. I'm quickly trying that one false side website to make a little image of this just to see what things look like, even though it doesn't calculate it quite right. The shape should still generally be okay, I think. It's really hard to get things to be symmetric with it, though. Huh.
Did you make all three of those the same magnitude?
Yeah, they're all three the same magnitude in this one. If I make them each half, though, what happens here? It almost looks right where there's almost like a perpendicular. Well, no, the equidentials don't even look slightly right. I think one of you should check the answer for Jerry's willing to guess. Oh, yeah.
The picture you got on screen right now. Oh. Yeah, I don't know.
Yeah, this doesn't look right, which I guess. Oh, you know, Fizzbuzz did say something about getting hyperbolas. That might be the issue. It isn't easy if you're looking at the right solution. Oh. Maybe I'll take a peek at the solution and I can, like,
Okay,
tell
if you
you
want
whether
to.
you want to. All right, look away from the stream, I guess, if you don't want to see it.
All right.
I mean, you're welcome to look at it too, but I assume you want to.
Yeah. No, that's fine. I'll let you peek at it if you want. We can do it
Okay.
that way.
Oh. Huh. Um.
Is it a case of
Wow.
where they have a picture that kind of gives away the game?
Uh. Yeah. I will say we were on the right track.
Okay.
Uh. But the idea is more complicated. Hmm. You're absolutely right about like the thing that I suggested just with the two mischarges don't work because they do interfere with each other, but there's a way that you can deal with that.
Hmm. What about if we had like 4 image charges?
That would help. You might still get some interference in that case though.
Hmm. think FizzBuzz said, don't put a charge in between, don't put any image charges between the plates, right? Did I read that?
Yeah.
The real region between the conductors. So maybe that's why they call it an image. You're sort of thinking of the conducting surface kind of like a mirror. Like you're gonna think about an image, right? Like the reflected image as if it was a mirror, a surface of a mirror.
Surface of the mirror. Yes.
So no image charges between the plates. Yeah, I don't know. Did you read the whole answer? Do you know how it works now?
I'm still trying to understand it. I have read the whole answer though. I need to read it a few times. It's kind of neat, but not what I would have guessed.
Okay, so is it so it's not immediately like apparent then?
No.
I thought it might be something where you just sort of look at it sideways and you're all of a sudden you're like, oh, it's so easy. But
it,
doesn't sound like it's going to be like that.
it's a different type of trick than that dipole one. It is a trick, but not necessarily a change of perspective.
Do we need to have like an infinite series of image charges or something ridiculous like that?
Yes.
Oh, you're kidding. Do we really? Because I thought about like, because when you put that one down, I was like, well, that'll interfere. We could put another one down to like fix that, but then that'll make an error and we'll have to go back and put another one down.
Yeah, and so
And kind of, some kind of series of charges.
you basically, yeah, you take the thing that like the first one that we drew and you duplicate it to left and right infinitely, basically. Well, I guess duplicate isn't quite right, but it like repeats symmetrically.
Oh, okay, wait. So are you saying so we have to just string it out along the horizontal line all the way to infinity, some kind of a repeating pattern of image charges. Oh,
So you get infinitely many equipotential like planes that are parallel, but we're only concerned with the two in the
that
middle.
actually that really does that makes sense, doesn't it?
Yeah.
I think that makes sense. It sort of feels like, we're trying to build a, like when you're trying to take a segment of a function and then you repeat it periodically and you can build it with Fourier series or whatever. It kind of feels something like that,
Uh, oh, I guess so. Where the more charges you
Yeah,
add on,
because
the
if
better
we,
approximation.
yeah, well, because if we keep taking the same, I don't, so what's it going to be? Is it going to be this sort of how you started, where you had one reflected with D and the other one reflected with L minus D, and then you just take each one of those and just repeat them with a cycle of L or something? Because if we or a cycle of 2L or some kind of cycle,
Yeah.
yeah, because then if you just go forever, then couldn't we argue that by symmetry? No, I don't know. I want to say we could just argue by symmetry that then it has to work. That the planes that sort of partition it have to have horizontal fields, but I don't know.
That's basically what the book does. The book doesn't do any actual calculation. It just makes the claim that, like, it calls it like a correction.
Hey
For
Brian,
each charge you
yeah,
want.
it's me.
Yeah.
Oh boy, that's tricky, isn't it? That's tricky. I don't think I would have thought of that.
Yeah, I enjoyed thinking about this problem, but I'm glad I looked at the answer because I don't think I would have gotten there.
Oh, I'm looking at your screen now on the stream. Yeah, I see the
Oh yeah, I'll
picture.
keep it
That's
still.
beautiful. It's pretty nice, isn't it?
Hmm.
So let's see. They did. They reflected. So we had it right away. We had the D into D and the L minus D to L minus D. And then you just take that whole thing and it's length 2L, isn't it? It's just periodic with period 2L. That's what it is, I think. It is. Yeah, I can see it. It's just because
Yeah.
L is the distance between those vertical lines. And so everything's periodic with period 2L. Yeah, doesn't that remind you of like Fourier series? I don't know why it's reminding me of that so much.
It's almost like a reverse Fourier series for like a step function. Like if you made these lines go up and down instead, it will remind me of like a step function. Huh.
It turns out that we will need an infinite number of image
yeah.
charges. Wow.
So, like, I guess now we know that this kind of infinite image charge thing, I guess, is an idea that can be helpful. Because
Yeah.
I think we were circling around this idea where you were saying we need to correct that, like, slightly not canceling. If we just followed that a little bit more and had that infinite charge idea, I think we would have gotten it.
In the special, right at the end, in the special case where the given real charge is located midway between the two planes, all the image charges are similarly located midway between the imaginary planes. So the net force on the given charge is 0 as it should be.
See, that would be periodic, I guess, with just L.
I guess that would have been the case where D was L over 2.
Yeah. All right. Neat problem.
Yeah, neat. Little hard, little hard.
Yeah.
Not surprising, right?
Mm-hmm. So the next one I had planned, let me look at it. Oh. There's a circuit one that I had planned for next. Unless you wanted to look at that other one that, like number 15 or whatever, but that was a 3-star one, so I'm a little bit scared.
Yeah, I'd shy away from that, honestly.
All right. Number 18 was proving the adding capacitors in a circuit thing, so that might be interesting.
Oh,
In series and in parallel. Oops. Brian wants parallel first. I don't actually know how you start this.
I think we have to think of charges and potentials. Yeah. The charges Q on the plates and the potentials. Because I do remember learning these theorems, or learning these rules for adding capacitors in parallel and series.
Mhm.
And I think that's how they argued it. They thought about Well, of course, when they did that in the circuits course, they'd already done all the stuff about resistors, you know, and Kirchhoff's KVL and KCL, all those things.
Right.
Whereas in this book, as it says here, we haven't even gotten to resistors yet. I guess resistors is chapter 4 and inductors is chapter 7.
Oh, looks like it, yeah.
How did they define capacitance again? It's a ratio of charge to voltage or something.
Yeah, charge divided by voltage.
Potential. Yeah, right. Okay. Okay. And they had formulas for spherical surfaces and then parallel plates, didn't they? I remember them talking about that.
Oh, here we go. So capacitance of the parallel plate capacitor. This way, want C equals epsilon not A over S. A over S, where A is the area of the plate, S is the separation. But okay, rather than the formula I wrote, there's a slightly different formula. When you're, whatever the question is for an isolated conductor, we have parallel plate conductors. V1 minus V2. I mean, technically absolute value of that.
Yeah, hi Fizzbuzz. Yeah, we're struggling here again with the Purcell and Morin.
We looked at the answer
yeah,
key.
yeah, yeah. We kind of had to. We needed help. We needed help.
Yeah, infinite series of charges. So
It's funny, you know, because I'd thought of that. I should have said something. Maybe if I'd said it out loud, we would have thought about it.
yeah, it's tricky. So the book only gave an example, like it gave basically the simplest example of using an image charge, and that was mostly it. So the idea of doing infinite makes sense that we can do it, but it never crossed my mind that it was possible. Yeah, the voice chat for these reading groups is open as well. If either of you ever wanted to hop on today or one of these Saturdays. In classic physics fashion, you want to go big or go home. Infinity is the biggest square there is. Yeah. You might do that one of these days. Oh yeah, no worries.
So are we supposed to assume these are parallel plate capacitors? I guess that when they draw it like that, does that mean they have to be parallel plates? I think that's what the
that would be mean if they
diagram.
weren't. I don't know the book ever like draws it as part of the chapter.
I don't remember it.
Oh, they do give an example of the capacitance of two spherical shells. Okay, that's probably helpful to see. Well, though. Okay, so they figure out for two spherical shells, they figure out what your delta phi is going from the inner shell to the outer shell with by integrating the electric field between them. And then the capacitance is Q over delta phi. So what is the field between two parallel plate capacitors? Isn't it just the field due to an infinite sheet of charge?
Um,
Oh, okay.
yeah,
Or phi1 minus phi2 over s. They say the field is. Which is still just a constant over, well, oh my god, I can never hit the right tool.
just gonna get the last of my coffee before it burns up on the burner
Oh.
here, so I'll be right back.
Okay. A basic intuitive explanation for capacitors in parallel. You wait for the word? Yeah, let us maybe think a little bit more. It's good to keep in mind, though.
So, I mean, we don't even, okay, well, they're saying C1 and C2, so the capacitances don't have to be the same. I guess the area, there's no reason to think that the areas of the plates would be the same or the distance between the plates either, right? I don't think we need to worry about any of that. We just need to think about the charges on the surfaces is what I would think of.
Agree.
So let's say we're doing what, so Brian said, let's look at part B first, right? So let's say we look at part B first. Couldn't we say, I mean, when we look at it, the upper plates of C1 and C2 have to be at the same potential, don't they? Because they're connected by that wire.
Oh, true. Yeah.
And the bottom plates are at the same potential as well. So we could call the top could be like VA and the bottom could be phi A and phi B maybe, or phi1 and phi2.
Yeah, I guess we can do. The book uses phi1 and phi2, so.
Yeah, let's do that. Yeah. Okay, and what else do we need? We need to know the charges, don't we?
Yeah, I should mention like the journey of like your test point charge, but like it's only ever gonna, a single charge would only cross one of these. But that's clearly not gonna be the case if we're adding the capacitances.
Let's see. Electrons want to go from high potential to low potential, right?
Yes.
So should we just assume, like, without loss of generality, that phi1 is higher than phi2 for now?
Yeah, sure.
And is it true that when you have parallel plates, is it true that the positive charge on one side has to be the same as the negative charge on the other side, right? I want to say that's true.
Pretty sure, or at least for the capacitors that we use in real life, I think the charge is always equal.
So could we say that capacitor 1 has like Q1 plus Q1 at the top and a minus Q1 at the bottom? The capacitor.
I think so, yeah.
I keep getting kicked out of this Excalibur. Is that happening to you?
Oh, no, it's working okay for me.
Probably my computer, and I got it on an old laptop that's kind of running out of memory.
Oh.
No,
Oh,
undo. How do I?
Control Z.
Just Control Z. All right, Control Z. There we go.
Oh, I see it's in the
So
bottom
I
left
think
as well. The actual button.
so. I think I must have written on the picture then. Okay, well, too bad.
I've seen pens that do that a lot. I think it's an easy mistake to make.
Yeah. What is this blue?
I definitely don't think I'm thinking about this right, because I'm trying to imagine. I'm trying to think about the potential, and that means bringing a positive test charge in on some path. And I feel like for part A, it should be we're adding the capacitances together.
Oh, you're looking at part A, right?
I mean, I'm mostly at part B, like we said we would do, but I'm just thinking I'm trying to figure out intuitively why we're just directly adding them in part B when I feel like that should be in part A, if anything.
So capacitance is a ratio of charge to potential, right?
Right.
So because the potential difference in part B is the same, right, for each capacitor, like we're going from Phi1 on top to Phi2 on the bottom. So yeah. I'm sort of remembering how they did this. I don't know. Should I write down what I'm thinking?
For it.
I feel like I got a little bit of a head start on this one because I've studied circuits a little bit. Why is it? Let's see. I'm still getting a blue. How do I change my pen back to blue? Oh, is it pencil? Oh, sorry, that's pencil. Number 7 is the pencil, right?
Right. And then in the upper left, you get the different color options.
It says it's black, but it's drawing blue on my screen. Try again. Yeah, it's blue. Well, that's fine.
Oh, yeah, that's weird. It's faded as well.
Or it's gray. Oh, wait. I had the opacity thing turned down. Sorry. I swear I'm such a noob at all this stuff.
Algebra is not very intuitive for me.
I'm just redrawing the picture down below a little bit. So, okay, so what I'm thinking is like we have Phi1 up here, we have Phi2 down here, and those are connected to those. The Phi1 at the top is connected to those 2 plates by wires.
Oh,
so.
Okay.
And the Phi2 at the bottom is connected to the bottom plates by wires, right? So what do we got here? C1 here. Oops. C1 and C2. And now I want to think of this as like Q1 plus up here and Q1 minus down here. And Q2 plus and Q2 minus. And now I want to think of this being like sort of isomorphic to this picture. right? We want to find, so we want to put everything in, let's see.
Oh, right. If the thing we're given is true, then we should be able to think of it as one capacitor.
Yeah, like everything in this red circle is kind of, this is like a black box, right? And we want to replace what's inside the red circle with a single capacitor.
Hmm.
Charged with capacitance C. Now, couldn't I say, yeah, because capacitance is ratio of charge over potential difference, right? So C equals, so I could call this Q. Yeah, here we go, Q plus Q minus. So couldn't I say Q over V1 minus V2? Okay, am I about to get stuck? Now what I want to argue and see if you believe this is true. I think this is true. I think I can say Q plus is the same as Q1 plus Q2 plus. Right? I think I can. I think
Hmm.
does that follow here? Because I think if we can say that, we can probably derive this. I'm kind of trying to argue that maybe at this point the plates have to be the same size or something. Is that true?
I guess we're implicitly
Maybe the
saying
three
the potentials
capacitors.
are the same. So if the potentials from either end of the circuit have to be the same, does that mean we have to have the sum of the charges? I guess, like, I don't know what else it would be. Hmm.
So I'm going to scroll down a little bit and I'm going to, oh no, it's just done this again. I got booted out again.
Oh no,
Dang it.
it's annoying.
Which means I got to scroll back down. I'm underneath the pictures now. I'm going to say,
I see, yeah.
I'm going to say C1 and C1 is Q1. No, it's crashed. Oh, no, we're still here. And C2. Stop me if you think this isn't, I'm not making sense here, because I could be all wet here.
Well, these two equations definitely make sense. That in terms of plugging into the formula.
So if those three equations there are good, right? This one for the one we got when we put them all together in the black box, and these two that we got for the capacitors individually, then I could say that the ratio C1 to Q1 is the same as C2 to Q2, which is the same as C to Q, right? Because every one of those ratios is just like the reciprocal of the potential difference.
Yeah, they're all equal to 1 over phi1 minus phi2.
Yeah, so now if because C1 and C2 were given, right? If we can say that Q is the sum of Q1 and Q2, if we can convince ourselves that that has to be true, then I think we can get it from here. But I think we need that extra step, because otherwise we don't have enough equations, right? I think at the moment we don't have enough equations to.
Yeah, I think we would define this Q to be Q1 plus Q2 and find that the capacitances work out. Is how I'm following this? Like
Yeah.
we're just gonna say that Q1 plus Q2. And then if you were to say add the equation for C1 and C2, I think we would get what we want.
Oh, yeah, you're right. I went right away, right? Yeah, it comes out. If Q1 is and plus Q2 is Q, then we've got it, haven't we?
Yeah. I think that works.
Okay, but why is Q the sum of Q1 and Q2?
In my mind, we're just saying that. We've created some other like third situation on the right that you put where you magically have the charges added.
Yeah, maybe it just has to be. What if I thought of like taking a sort of a plane, whoops, not necessarily a plane, but a surface that sort of goes in between the capacitors here like this. So I'm taking this dotted line here,
Okay.
and I'm saying that dotted line there, couldn't I draw a parallel between this dotted line and the second setup? And from the point of view of the potential difference, phi1 to phi2, phi1 doesn't know like where that red line is, right? Phi1 and phi2 are just noticing that they're different and they're trying to push electrons. And how many electrons are they going to push? Well, I think it's just some kind of how does that work? Because I'm trying to wonder, do we need these capacitors to all be the same like size? You know we had the formula in terms of A and S, like A is the surface area and S is the distance between them.
Mm-hmm.
I'm a little worried that we need to know something about that A or that S to be able to finish this.
Hmm.
Brian says he thinks that works.
This makes sense to me, holding all these capacitors to be physically the same. And the only thing that we're changing is the charge that they hold. But I've always been pretty terrible with circuits, so my intuition is not good. But yeah, Brian, you said you have that way to like think about it, but it might be a good time to talk about it now.
Oops. Sorry, I just muted and unmuted myself about 10 times in a row really quickly.
Oh, no worries.
I've seen this kind of argument in circuit theory books before, but I don't know if we need a better argument because this is not circuits now. This is actual electricity and magnetism, right? So maybe we might need a better argument than this one I'm coming up with.
I mean, I don't remember seeing a theme like this written about in chapter 3, but it's also, they didn't talk about circuits really at all, I don't think. So,
No. No, I think they get into circuits in a later chapter.
yeah. Unlocked. You're right, I have shorts. Boom, called it. Oh, I didn't even see this example. Capacitance coefficients for two plates. Oh, this actually seems pretty relevant. Maybe we're supposed to repeat this examples technique. Two of the exact same parallel plate capacitors with the same voltage will hold twice the charge. Capacitance is also proportional to area, so it's like adding areas. The dielectric part, I think we can just take as being the same, so we haven't gone to that in the book yet.
Yeah, you know what? I think what I did down there will work.
Okay. Can we do a
Because,
similar argument for the
capacitor.
first one? Oh, sorry.
Yeah, we could do something similar for the first one. They want the effective capacitance. So they're basically saying, what's the ratio of the charge to the potential difference, right? I mean, that's all you can, if you're asking what the capacitance is of the black box, you got some circuit in a black box and you're like, what's the capacitance of this black box? All you can do is say, what's the ratio of the charge on the top of the black box, the charge on the two plates divided by the potential difference. I think it's fine. I think it's okay.
Okay. Also, having two capacitors, same capacitance, is doubling the area and thus the capacitance. That's a nice way of thinking about it.
Yeah, because you got twice as much plate to work with, right? In
Yeah.
fact, the picture for part B, you can almost imagine like if you push the two capacitors closer together till they touched, it would just be one big capacitor, right? You sort of, if that was physically possible.
It'd be nice to do an analogous calculation for, I guess, part A.
Yeah.
And I assume the trick is going to be define on the right side, we're going to have to name something else for our charge Q. Oh, well, this isn't P1 minus P2, is it? We need some kind of like intermediate P sub 3?
Yeah, now we're gonna have something in the middle, aren't we?
Well, we could notice that we could have V1 minus V3 plus V3. I don't know if this will be helpful, but oops. We could make a grouping like that in the resulting capacitance.
Hmm. Yeah, I like that. I like that.
Um,
Yeah, now you could use your definitions of C1 and C2, right?
oh, I didn't, yeah, okay.
The C2 as a, what about the denominator of C2 there? Is that right?
Oh, no, it's not. So be Q1 over C1 plus Q2 over C2 is equal to C.
Oh, that's looking really good.
It's nearly there, yeah. For this to be true, all the Q's have to be ones? Oh wait, no, we're not, isn't quite. Actually, it is what we want. We just need the Q's to be ones. I think.
Ah, yeah. Well,
I don't know how we justify that.
actually, I got an idea,
Oh
yeah,
yeah,
for
go on.
how we can. Well, I don't want to give it away, but if you look at the two pictures you drew, the left one and the right one, take a look at the left picture, right? The one with the two capacitors in series.
Mm-hmm.
Don't we know something about the charges in this picture?
Oh, they should be, if they're the one, this connection here means they should have equal charges on those
Yeah,
two
that's
inner
what I'm.
plates. Yeah.
Yeah. Okay.
So maybe we want to take Q equals to twice. I don't know if that's what I want.
I
We
don't
know
think that's
Q1
what you
equals
want.
Q2. Okay.
Yeah.
Oh, and so, okay. Um, say Q, maybe, I guess equals Q1 equals, I'm afraid that we're going to get, no, we won't get a doubling. Okay. Oh,
Yeah, I think that's true.
because we
I think
can,
they're all, I think all the Qs are equal, I think.
yeah. So you can back to the Q out, they cancel,
Yeah.
and then we can flip both sides.
Yeah.
Okay. We'd have to check some limits as well, I guess, but it's neat.
Say that. Can you say that again?
That's part of the problem. They said to check some limits.
Oh, that's right. We didn't check the limits. Yeah, that's right. There was more to do. Okay.
C1 goes to 0 and C1 goes to infinity. Oh, I guess the point is how the overall circuit behaves differently depending on one of their capacitances.
What does it mean sort of physically to have infinite capacitance or zero capacitance?
Uh,
I remember in circuits, you're always talking about like opens and shorts, you know? So if you had a short circuit, you'd have like zero resistance and zero potential difference. I feel like we're gonna have one of these is gonna be like an open circuit, and one of them is gonna be like a short circuit, like just having a wire with no capacitor, or just like pulling the capacitor far apart so that it can no longer really be a capacitor.
Yeah, I guess if you have zero capacitance, you can't really store any volts no matter how much charge you put on it. Or you don't store volts, but I guess joules. If you have infinite capacitance, I guess you're really... I mean, I guess you just close the circuit completely. I don't quite know what it means for the circuit, but... I guess going back to the answer for part A. If C1 goes to 0, then this limit goes to infinity. It doesn't matter what C2 is. I guess that seems like a short circuit. Like you're getting a whole ton of volts for no charge.
That was I think that was 1 over C though, that you had down there.
True. Infinity. Oh wait, so you're right. It should be equal to 1 over C. Then that kind of messes with that interpretation, doesn't it? Maybe it's easier to do the flipped version.
Wouldn't that just mean C goes to 0 as well?
Yeah. So if one of the capacitors in series is infinite, then you have 0 overall capacitance, apparently.
That feels like that has to be like an open circuit then. Maybe C equals 0 is like an open circuit.
I think so.
Yeah, because based on the first equation you wrote down, right? Q equals C times phi1 minus phi2. So if C is 0, that means Q is 0. And it doesn't matter what phi1 and phi2 are. So we could have like a big potential difference, but we're not pushing any charge at all, right?
I think so.
So that feels like it means it has to be an open circuit, I guess.
Does capacitance increase with distance between the plates? It decreases, which is probably your point. Or, well, the bigger the distance, the less the capacitance. So I guess you could think about it like if you were to get infinite capacitance, it would be like smushing the plates together and having 0 separation. Which I feel like just makes it a wire.
Oh, yeah, if S goes to 0, that means we push the plates together and C goes to infinity. And that's a closed circuit, or a short circuit, they call that. Because it would, like you said, Don, it would just turn into a wire, right? If we let the plates touch each other.
I guess so, yeah.
Okay. That's cool. I like that. So, right. So if S became 0, the capacitance would go to infinity, and we'd have a wire. And if S goes to infinity, the capacitance goes to 0, and we got the plates infinitely far apart. So it's like it's not even it doesn't even exist anymore.
Yeah, it's the opposite of the actual result you get for the limit, though.
Is it?
Because if you take C1, if they're in series, and you let C1 go to infinity, you just get C2. I feel like we should be getting 0.
Infinite
Wait,
capacitance meant 0 distance between the plates, right? So C goes to infinity. Let's write it down so we know it. So C.
Okay, I had to reverse, I think.
Yeah, it's easy to get it backwards. It always felt to me like capacitance is defined like inversely of what you would expect it to be, you know, because there's all these formulas you learn in circuits for like resistors and inductors, and they all sort of work the same way. And then capacitors kind of feel like they're backwards somehow. Feels like everything's upside down. Let's see, Brian's saying C1 goes to infinity, then C is C2. Yeah, that's what we got, right?
Okay, when I actually like write it out as a reminder to myself, this now makes sense when I'm looking at it. That if we just have a wire, we should just get C2. Because we just have one. Okay, yeah. Okay.
All right, that's cool.
I guess then for part B, I went over to the left for this. If we let C1 go to 0, C1 plus C2, we just get C2. And so this is if we were to let S go to infinity, which is basically we're disconnecting the left half of the circuit.
Yeah.
Oh yeah, and then now if we bring the left part close together, so it just makes a wire, then we're bypassing the capacitor, we're bypassing C2 completely. It feels like a short circuit.
Yeah, yeah.
Okay.
All right, cool. Yeah, he even says at the end of the problem, these two rules are the opposites of the rules for adding resistors and inductors.
Yeah, it still feels weird to me, but we proved why, I guess.
Have you seen these theorems before, Don? These adding like capacitors in parallel and series?
Not for a long time, but I did learn them at one point.
Yeah. Because this is part of physics too, right? I mean, I think this comes up in physics too somewhere, briefly.
Yeah, I mean, I even learned a little bit about circuits in like my high school physics class.
Yeah, nice.
So I think we learned those then, for sure.
Well, do you want to check the answers? I feel
yeah.
very confident about this. Yeah.
I was in AP Physics C. Didn't even know that.
Physics C.
I think
There
it's
might not
basically
even be
avoided
any
AP.
answers for this one because this one was just like show. I mean, I guess he has to have answers, right?
We got something here. The charge on the top plate of the bottom of the capacitor must be the negative of the charge on the bottom of the plate. Okay, yeah. So for the series one, they noticed the same thing with the charges having to be equal.
Yeah.
Okay, and they do basically the same calculation. A little bit cleaner, of course, but... Oh, they don't even relate this to like a short circuit or an open circuit.
Yeah,
That's
well,
interesting.
maybe I shouldn't have been talking about circuits so much. I just, when I see a question like this, that's where my brain goes.
Yeah, I like being able to like put it in those terms. But let's see what they said for part B. The voltage drop from the top of the overall circuit to the bottom can't depend on the path. That's the argument I think you were making with that red line.
Yeah. Yeah, they just said the total charge on the effective capacitor is the sum of the charges on the top plates of the two capacitors. They just basically said it. I felt like that had to be right.
Yeah, I they just kind of state that that's true. Which doesn't
Well,
quite sit
because
right
I
with me,
think
but oh,
I think, like I said, I think the way you want to think about it is if it's as if it's a black box, you know, like the when I drew those two pictures in the left one, I circled it with that red line. You kind of want to imagine that red line's like a black box, and you can't really look inside it, right? So you're outside it, and you can measure the node voltages at the top and bottom wires, and then you can have some kind of an an electron detector or something, so you can see how many electrons go from phi1 into the black box, right? And you can see how many electrons to come down out the bottom to phi2, and you can count those electrons, and you can argue that, well, we don't know what's inside the black box. It could be picture one or picture two, but it has to be the same number of electrons in each picture, right? If it's an equivalent circuit.
oh, okay.
And those electrons that come down, you know, on the right side, on the right picture, they just all go to the single top plate. But in the left picture, they can choose which way they want to go, and some of them go left and some of them go right. But ultimately, it's the same number of electrons, right? I think that's the argument.
Yeah, and that would also explain why in the situation with this them connected in series, they're all equal.
Yeah. You know, I
Okay.
remember when I saw, because the book I read, or one of the books I looked at that was talking about capacitors in series, it didn't just have two in series, it had like, you know, N in series or whatever, a whole bunch of them in a chain.
Mm-hmm.
And I remember thinking it was really cool that the same charge sort of dominoes down through all the plates, you know, it's like you push some electrons onto the top plate, and then it makes the electrons on the bottom plate get pushed down, induced like an induced current or whatever, and it's sort of like dominoes all the way down through all the different plates.
Interesting.
Yeah.
As we're seeing from the above series, such parallel rules are the opposites of the rules for resistors and inductors, but there isn't anything too deep here. C prime defined by phi equals C prime Q. Oh, just flipping our definition of C. They're okay, I guess they're
Yeah, see,
saying okay, yeah.
and that's kind of what I was saying. I never really understood why they didn't do that. It just felt like that would have made, but I'm sure there's some situations where they don't want it to be defined that way, but I don't know why.
Yeah. I guess it's just a derived thing, so you could define it either way you want. But yeah, there must be some advantage to doing it that way. Hmm.
Well, we got two problems done.
Yeah, I mean, I'd say we, but you did really well in that last one.
Well, like
Um,
I said, I felt like kind of a ringer on that last one because I took a circuits class not that long ago. During COVID, I took an online electrical networks course, and I've always been interested in circuits. In fact, just last year I read a bunch of electrical networks textbook that my dad had.
Oh wow. Yeah, I remember you said at one point that you studied circuits recently. So I think that's part of why I chose this problem.
Oh, thanks.
I didn't realize you studied them to like that level though. But yeah. I guess
All
we'll
right.
wrap up
Well,
the
I
reading
guess
group. Yeah.
yeah, we went over, but thanks for having me.
Yeah. Thanks for being here. Talk to you later.
All right. Yep. See you next time.
Bye. Okay.
Nice little session there. I'm gonna need a minute to switch over to math. What music am I gonna play? I feel like listening to this right now, I guess. Why not? All right, before I forget, let me export this board we just made. Yeah, Brian, thanks very much for giving your thoughts there. The entire point of this for me is to have like work together on things, so it's always nice to have people that are like interested in actually like talking about this stuff, because it is pretty like mathematically intense. Notes, or like not even necessarily the math, always just like conceptually intense too. Notes for chapter 3 part 2 meeting. Okay, I got the notes uploaded. Being wrong. I mean, I haven't been right yet, I feel like, so I can't judge. Yeah, I might want to take a quick look through the book to see what all image chart problems there are, because I might want to pull another one. That's not that 3-star one. Still getting things switched over though. I bet in whatever the second half, like the problems or exercises, there should be at least one more, I bet. No, 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 no. Okay, God, I need to see if I can automate this stupid YouTube title and like, I almost certainly can use StreamerBot to automate this annoying part of the stream. I just need to actually look into how. Anyway, I think I'm all switched over on both YouTube and Twitch. I don't think there's any math questions waiting in the Discord. In my Discord, anyway. So let's take a little look at the rest of the problems in chapter 3 and see if there's something else with image charges besides a 3-star. I might be interested in attempting this 3-star at some point, but even the 2 stars are pretty freaking tricky, so. Oh God, a classic Brian problem. Oh, you know what? We were talking about I forget what was there. I remember Milk and Horns are there. Fenlux might have been there too, but we noticed that 69 is equal to 6 times 9 plus 6 plus 9. And I think Milk said that works for any multiple of 9s. And that was kind of like a neat format to write something. Or not necessarily any multiple of 9, that doesn't sound right. But there's a kind of like neat pattern word that works for a bunch of different numbers. Let me, okay. We have 6 6s times 3. We can, oh, is the prime factorization of 6 6 6 6 really easy? Can we just say it's, no, we can't. Because it's 6D, not 6 in the tens place. Or, well, wait. Okay, you know what? I'm gonna go to the works. I want to see if I can figure out the trick here. This is no longer quick math, but sue me. What I want to do is say this is 6 times 100,000 plus 6 times 10,000 plus 6 times 1,000 plus 6 times 100 plus 6 times 10 plus 6 times 3. Factor out the 6's, and you get 111,000. You get all 1s. Which I guess I didn't have to do that first step. I could have just said that 6 is, or that's 6 times that, but I'm already here. Does that actually simplify it though? We can make the problem times 18, but is this easy? I don't know what the trick is, I guess. We could say it's 8, 8, 8, 8, 8 plus that? Splitting the 18 into 10 and 8? And then this isn't so hard, right? 1, 9, 9, 9, 9, 8. Oh. I think that's the answer. I don't know if... Is that the trick I was supposed to use there? I don't know if I would have been able to do that in my head. I probably could have. After seeing it actually like written out there. Oh. That's a crazy idea, Fenbox. I would never have thought of that. There are many possible tricks. One is 1,000,000 minus 1 times 2/3 times 3. Oh, okay, and that's actually the same idea that Fenbox thought of. Because that would boil down to 2,000,000 minus 2. Wow. Neat. I mean, I don't think I would have noticed either, but like I don't think I would have noticed either of those tricks, but It is a nice trick. Oh, right. I definitely grabbed, I think 31, because this figure I guess both of them look so interesting. Putnam 1998 A1. Is it, this is like a geometry question. Does it use a trick like that? Students in Calc 2 how to work out numbers like 1.2345. I imagine it's something involving 7. I don't know how you actually do that though. That doesn't, well, I don't imagine that's it either. History has changed. And with repeating the, oh yeah, you know, I think I've seen a trick and I immediately forgot it after seeing it. Oh yeah, you know, 30, I don't think that I grabbed it, but 32 looked kind of cool. What is wrong with the idea of a gravity screen? Something that will block gravity the way a metal sheet seems to block the electric field. And I think that's because there's no such thing as anti-gravity, as far as I know. You know, there's no like negative charge equivalent to cancel. There's no like negative gravity that cancels positive gravity. I assume that's all you're going to say for 32, but try to solve this without doing any calculations. That sounds like a nice way of solving it. Not having to calculate anything. Images from 3 planes. I'm gonna pull 43. This is a crazy image charge problem. Oh my god. I'm gonna add it to the list of ones that seem cool. Uh, 43, comma. There we go. 98 B5. And be a decimal integer, all ones, with 1998 digits. What is the 1000th digit of the decimal point of the square root of n? Oh my god. Does that really avoid a copyright problem? Isn't the substance the important part? I don't actually know how copyright works, I guess. Oh, do you have to split this number up into a perfect square? Like something plus something squared? Well, is that even possible? Ten to the 1998 minus 1 over 9. Oh. So you can take a 3 out of that square root. I don't quite know what you do. That 10 to the 1998 minus 1 is still trapped under the square root, though. Unless you can just... I mean, no, you probably can't approximate the thousandth decimal. That. Ooh, a dreaded 4-star problem. They didn't even give a solution for it either. Oh, really? Okay. Hey, there's another image charge problem. Actually, let me put it in a separate line in my original Discord. It's a bonus image charge problems. Because they were fun. 43, 46. What actually exists? Another 4-star? Oh, you're saying the 4... I thought you were censoring a curse word. There's one in chapter 2 as well, I think. Hmm. Huh. Yeah, problem's crazy. Oh yeah, I only saw 2 other image charge problems, it seems. Oh well. As much as I kind of... I mean, there might be more that I just, like, didn't bother to read the text of, but, well, I could do more physics. Maybe I should do algebra. Infinite reflection problem? Yeah, it was 2 stars. Oh yeah, here's a 4-star in the exercises, or whatever the first set is. Yeah, it's like in chapter 1, we like the 3 stars weren't so bad. But the farther we've gone in the chapters, like the ones in the 2 stars are the new 3-star. I guess in chapter 1 there's just less things that you can ask about. Yeah, the scale is 1 to 4. So 4 is the max, 2 is, I guess, like medium. If it goes easy, medium, hard, impossible. Actually, what were the Guitar Hero difficulties? I think it was easy, medium, hard, expert. I know we did some 3 stars in chapter 1. I feel like we did at least. Dude, after playing Portal yesterday, I had to think so hard that like my brain was sore after it, and I don't feel like I've completely recovered. Even today, the physics didn't help. Even though it was fun. Probably not gonna be able to stream for like a ton longer, but I would like to see if someone comes in and asks a math question. Chapter 6 for tomorrow night. Oh yeah, Penn's about to move on. Oh wait, no, Penn's already moved on. I remember seeing him doing isomorphisms last abstract algebra stream. I remember being very confused. Well, there's like, you can have like ought of a group, you can have in of a group. Some of them. I'm probably not going to go through all the chapter 5 problems that Penn Center assigned, but I feel like I need to do a couple more. I'm looking through to see if they talk about subgroups of permutations, which are really annoying to think about, because a subgroup isn't a particular permutation. It's still every like possible set of permutations, just not the same as the bigger group. Do they never say anything about subgroups? I guess they talk about the even, like the A group. Somewhere down here. The set of even permutations in S sub n forms a subgroup of S sub n. And we call it A sub n. Oh. Is there a non-cyclic permutation? Maybe if you have like an infinite set, but if you have a finite set, do they? I feel like they talk about this. Yeah, I think you make some kind of argument about like decomposing it into the, what do they call it when you only swap two things? The two cycles? you can make an argument for something like that, that it has to be cyclic. So at least they say in the book that they're only focusing on finite sets. You don't think it has to be cyclic? So, yeah, true, you can generate a cyclic subgroup, but what will be a non-cyclic permutation group? All cyclic groups are isomorphic to, well, that doesn't mean all permutation groups are cyclic, though. Hmm. Oh well. I guess I'll... It sounds like they're not necessarily cyclic, which I guess I should just try to remember. Oh, wait. I get it. Yeah, no, it doesn't have to be cyclic. You could have... One, two, three, four, 2, 1, 4, 3. None of these swaps are going to generate the entire group. Okay. Yeah, never mind. I was thinking about it more, and it's like, that isn't right. But does a cyclic group have to have every element be a generator, or just contain a generator? Well, if it contains a generator for the entire group, then every element must also be a generator, right? So did I show that S sub 4 isn't cyclic? Because I can name a group an element that doesn't generate it? Maybe that's the proper way of phrasing this. Wait, no, I don't know. I'm thinking about this wrong. Oh, not every element has to be a generator? I don't know, man. Yeah, right. It isn't... Right, not every element has to be a generator, because, like, it has to be relatively prime. That's the rule to the integers, at least. But I think S sub 4 still isn't cyclic because I can make the claim that no generator can possibly get this. Well, no, never mind. I don't know. I don't think my argument works. Somewhere on like 23 or 24, I think. Probably 23. Right, yeah, I think it was on 23. Because I remember, like, because of the subgroup, I was trying to look up what we know about subgroups. So for the first part of this OR, we already know that A sub n is a subgroup of S sub n. So I think that solves the first part for us. The second part takes some thinking. Why would it need to be half even, half odd in order to be a subgroup? Because if you take an odd permutation and multiply it by an odd permutation, you get an even permutation. So you can't have all odd. Can't be a third? No. But why exactly half? Because I imagine, this isn't really a proof, but like, if you want to take a subgroup of like a S sub n, I think it would have to be like, say, every permutation that holds 4 fixed. And then you basically have S sub 3, but with an extra, like, extraneous 4. And are those exactly half even, half odd? Is S sub n? Yes, we do know. Because of this. A sub n is order n factorial over 2, which implies, or, you know, it's only half the permutations of S sub n. So S sub n is half even and half odd. And if you take a subgroup that just holds an element fixed, then you essentially have S sub n minus 1. And that is also half even, half odd. Okay. This chapter is really difficult. Because I'm not a fan of with permutation groups. Like they're probably helpful for something, but they're very hard to think about for me. So I feel that, Brian. It's an odd number. I kind of want to check the answer, but I think I have the idea. Chapter 523. Suppose H contains at least one odd permutation sigma. Oh. Theorem 5.7 with sigma in place of 12. Oh. Okay, well, I guess I got the idea exactly then. They're all possible functions on n elements. A cool way of thinking about permutations. Oh, okay, yeah. I guess that's fair. Okay. Satisfied with answer for 23. What's 24? Suppose H is a subgroup of S sub n of odd order. Prove that H is a subgroup of A sub n. Really? How do you have an odd order subgroup yeah, I think it's only S sub 3 works. Because I'm thinking like the order of S sub n is n factorial, and you're guaranteed by being a factorial to have at least a 2 in there for n greater than or equal to 2. Really? Those are... Okay, this... Yeah, okay, the subgroup generated by 1, 2, 3, 4, 5, I guess. That's really... Okay, the reason that... The reason that that's okay is because they say the order of S sub n is n factorial. And so I was thinking, because of that factorial, we're guaranteed, you know, at least 1 power of 2. But when we talk about groups generated by an element like that, those are no longer S sub n. That's something else that the order you have to calculate. Okay. So you can say that those subgroups you all are putting in chat are a subgroup of S sub n, but they're never going to be, you know, S sub k or, you know, some other definition of S. And so I assume the pattern here is that if it's an odd order, you have an odd number of things written in those cycles. 1, 2, 3, 1, 2, 3, 4, 5. Those are odd numbers. And then right at the end there, you have 3 and 5. Use exercise 23, Zone Ranger says. Every member of H is even. Or exactly half its members are even. I guess so. So we want to show that this second possibility can't happen. So it must be that every member of H is an even permutation and therefore a subgroup of A sub n. So if it has odd order, we have to it can be broken into every element of H. Well, okay, if it has odd order, then every element of H can be broken into well, wait. If H has odd order, then H is, every member of H is can be written as the product of odd cycles. Or an odd, can be written as alpha 1, or no, alpha. How do you write an, I want n cycles, but like it has to be odd. Like how do you write that? Don't mix up odd order with odd permutation. So I'm going to make the argument that because of the LCM thing, right? Because of the LCM, it has to be made of odd number cycles. Not necessarily odd permutations, but I want to, where is it? This thing here, like you can only have every number being odd. I guess like that. Yeah, using theorem 5.3, you know that the disjoint cycle form must only contain odd cycles. I'm not phrasing it right. Disjoint cycles. And then from here, I mean, I just want to say that if you have odd disjoint cycles, decompose, I don't know if that's the right word, into an even number of 2 cycles. Hence, every member of H is an even permutation. I assume there's an easier way to do this using exercise 23 directly, but this is where my brain goes. For a subgroup of A sub n. It's like a similar theme, I guess, but I didn't really refer to exercise 23 directly. If I'm making the claim that if it has odd order, that implies it can only be written as the product of odd disjoint cycles. Because the order of the group is the LCM. So if you have an even cycle, your LCM is going to be even. I think. I hope. Yeah, it has to be a common multiple. But yeah, I'm just thinking like the order of a permutation of a finite set. Maybe I'm not applying this theorem right? The order of a permutation of a finite set. What does that actually mean versus the order of a like what is why are they saying finite set rather than is that talking about a single permutation? Oh crap. I think it's talking about a single element. Hmm. Yeah, maybe I actually just used Lagrange's theorem by accident. Which maybe I should just figure out how to apply exercise 23. It's just this. Distinguishing between a subgroup and an element is it's just so hard for the permutation group for me, I guess. You're trying to actually do something like this. Because I can see from the examples that you all put in chat before that, you know, 1, 2, 3 decomposes to an even number of 2 cycles. 1, 2, 3, 4, 5 decomposes to an even number of 2 cycles. And any multiplication of odd cycles comes out to be an even number of 2 cycles. But how do we, if it has odd order, must it be a cyclic group? Is that how we make the connection? but it's a subgroup of A sub n because no matter which element you want to choose, those are all even permutations. Which I guess you probably know, but I'm like... If we can just say that H is generated by a cycle like what you put there, I don't know. There must be a more direct way to do this with 23. Like, if exactly half its members are even, what does that mean for the order of the group overall? Does it have to be even? I don't know why, though. Like, I know that has to be true if we're able to use exercise 23, but... How do you relate the orders of the elements to the order of the group, I guess? I thought we do. Like, if a group is composed of half even and half odd permutations, I don't know what that means for the order of the group, I guess. I know what it must mean, but I don't know why. Hmm. Well, that's the thing. I don't know what to do with those. With those numbers. Like, I don't know where to even start with that. Like... Oh. Oh, okay, Stall. Thank you so much for the prime. Holy crap. I really appreciate it. Now I feel all self-conscious about being agitated at algebra. I should be cheerier. Yeah, I love that movie. How did I justify 23 again? I think I did. Oh, right. Ryan's private savings in good hunting well. Permutations of popular movie titles? Oh no. They're odd permutations too. Or no, those you only switch two words. That's in no? Yeah, they're odd. Wait. Saving, private. No, never mind. I don't know what I'm talking about. My brain doesn't work. Yeah, that's why I justified 23. $24. If it has odd order, all of its members must be even. It has an odd number of permutations in the group. Oh. Oh, that's stupid. You can't have half an odd number? Is that the entire argument? Okay. I was making it a lot harder in my head, I guess. I feel cheated. I thought it'd be like... Okay. You know, I just got purcelled. I was trying to do it the hard way when I should have done it the easy way. Oh my god. Next one was 27. I think the theorem that I cited is wrong. Because that theorem 5.3 talks about a single element of the group, not about the entire group. But it would have been right if we're allowed to use Lagrange's, I think. All the permutations in a group of odd order. Well, wait, is that necessarily true? Oh wait, yes, that's because of what I said. I just really like the idea of decomposing it into 2 cycles, I guess. So I try to lean on that. I guess I think a default for me with this chapter is to bring things to 2 cycles. Because an even number of 2 cycles, if you, yeah, it implies if you were to like collapse them all back into one big cycle, an odd number of things. How many elements are there of order 2 in A sub 8 that have the disjoint cycle form? So what they did here, and the one that I was trying to use in the last problem, these are the possible orders of the cycles, but not the number for each order. Okay, so something like this. Oh, counting. Oh no. Oh, hey, 420. Oh, that's a friend's favorite math joke. 2 math majors argue and bet whether people know basic math at a diner. One goes to the restroom and say their calls over the waitress. Say a third x squared to whatever I ask. The other returns the table and the seated one asks the waitress what is the integral of x cubed, to which she replies a third x squared. Seated one says I won the bet. As the waitress turns and shouts plus C. Oh, the mathematician isn't the one who knows math. That is pretty classic. Okay, I think this example is going to be helpful. I assume we have A8 though, rather than S8. But does that matter though when they're asking about the form A1? I feel like it's going to be the same. Is this 8 factorial over 4 factorial? Because there's 8 factorial ways to choose. Ooh, do we need a sneaky, like, 2 to the 4 in there? I'm thinking for A1, A2, there's 8 times 7 ways to choose those. But you need to eliminate the case, or it double counts. 2, 1 is the same as 1, 2, but it counts those as different things. So I think we need 8 times 7 over 2 times 7 times 6 over 2 times basically 8 factorial divided by 2 to the 4 divided by 4 factorial. Or probably a better way of saying it, 8 factorial all over 2 to the 4, 3 factorial, 4 factorial. And the 4 factorial is to eliminate, or is because these things commute. And we need to get rid of those, the different orders of the entire, like, 2 cycles. You think that's it? Let's see, it's an odd number, so. Eight factorial, 2 to the 4, 4 factorial. All right. I actually did a counting problem right for once in my life. Because I was able to just mimic what I saw in the example. All right, I was going to do like one more algebra problem. Number 30 is next in Penn Center's list. Prove that 1, 2, 3, 4 is not the product of 3 cycles. Generalize. Um, they don't even say disjoint 3 cycles, which is weird. That thing with the partitions relies on disjoint cycles. Yeah. I don't think that's going to help them. It might be this. Because if you have something... Yeah, I think it's... I think we use that. Theorem 5.5. Let's write it out though, not be lazy. Playlist looped. We found the order of the permutations of this playlist. One, two, three, four can be written as the product of 3 2 cycles. Wait, I need to reread theorem 5.5. We need some metal. I can play some metal. You don't have to ask me twice. I want to get Pantera. We'll turn it up a little bit. Theorem 5.5. The permutation can be expressed in an even number of 2 cycles, and every decomposition of alpha into part of 2 cycles must have an... Gojira the other day. They did? That's awesome. I found them because they opened for Slipknot, and they were way better than Slipknot. So ever since I saw them live, I started listening to them. I want some merch for Ginger, my favorite metal band, but I don't like their merch as much as I like Gojira's. I need to check their store again. It's been a while since I've checked it. Be a good chem/music pun for metal. Probably. I don't know it though. I just need to reread Theorem 5.5 and focus for a minute. Information alpha can be expressed products even. Every decomposition of alpha into a product of cycles must have an even. Okay, yes. Not necessarily the same number of 2 cycles, but both even and both odd. When that Gasso took my youth and gave it all away. By Theorem 5.5, every decomposition of 1, 2, 3, 4 must have an even number of 2 cycles. Suppose 1, 2, 3, 4 can be written as the product of 3 cycles. Then 1, 2, 3, 4 is equal to alpha 1, alpha 2, alpha 3. Do I want the same alphas? I guess we can just use different Greek letters. It doesn't matter. You left me incomplete, all alone, but the memory still remains. So the issue we're going to run into here is that these 3 cycles decompose into an even number of 2 cycles. Well, two cycles. Since the product of 3 cycles decomposes to an even number of two cycles, 1, 2, 3, 4 cannot be written as the product of 3 cycles. And so what's the, what am I spelling? Cyclicals? We do need to do the generalized part. Oh, I've heard that one. Why don't wind turbines like classical music? Because they're huge metal fans. Why do jailhouse orchestras suck? They're always behind bars. Oh god. So, generalization for even n, an n cycle cannot be written. Let's get a better song of this. You know, let's get some Gojira. Time flies like an arrow, fruit flies like a banana. Oh yeah. Flying Whales, classic Gojira. Could you write? So these were all always 3 cycles. Could you have it be different? Could you have it be written as all odd cycles, not necessarily just 3? I think the answer is no by the same argument. So we can generalize a bit further than keeping them all the same length. Even if you were able to mix like 3s, 5s, 7s, it still doesn't work by the same argument. I guess maybe as a product of odd cycles. I don't know if that's the proper like way to describe it, but can we say the reverse, that odd n can be written as the product of even cycles? Maybe not. Because if you have no, because 2 is even. If you have 1, 2, 3, you can write it as a product of all even cycles. So the reverse is not necessarily true. Right? A STEM joke day? Some kind of like comedy night or something? Hey, Tommy. I'm trying to think about the last thing that I concluded there, that the reverse isn't necessarily true. So I feel like I may be doing it slightly wrong, or thinking that's slightly wrong. There's a comedian who does science stand-up and has a series of walks into a bar jokes. The last one is Schrodinger's cat walks into a bar and does it at the same time. This is bothering me. Why doesn't this work in my head? I think it doesn't work because an odd plus an odd is an even, whereas an even plus an even is always an even. That's what makes me think it doesn't work, but I'm trying to actually justify that. And proving the same logic isn't helping me right now. I mean, we always know that every n cycle can be written as the product of disjoint 2 cycles. Does that already defeat any hope of... That must defeat the odd length cycle being unable to be written as even cycles, the product of even cycles. Do you think it's generalization that they're looking for? Okay, it's an even number problem, so I guess... I might Google it just to confirm, because I'm not feeling that confident, but I'm pretty sure that you can't say that the reverse is not true. What did I just do? I think I made my Firefox browser 0 size in OBS, and I can't find it anymore. Transform, reset transform. There we go. Problem solved. Prove that 1, 2, 3, 4 is not... Oh, hey. Joint pain or disjoint pain? Brainly? Are you gonna make me pay? You're gonna make me pay. Well, they don't generalize. Okay. I think I'm just gonna maybe live with my answer then. Or maybe I'll be able to say that definitely no one have more brain power. I think I should wrap things up for the day there, though. So we have the YouTube stream up here. If you're here on YouTube, I appreciate you. I'm back on YouTube on Tuesday. And goodbye, YouTube.